Hello, in this example, I'm going to be working through our Chapter 8 in-class example, problem number 1, which states, a sample survey of 54 discount brokers showed that the mean price charged for a trade of 100 shares at $50 per share was $33.77. The survey is conducted annually. With historical data available, assume the known population standard deviation of $15. Develop a 95% confidence interval for the mean price charged by discount brokers for a trade of 100 shares at $50 per share. When you're being asked to conduct or create a confidence interval, we have 3 different formulas to pick. We have confidence intervals about the mean, which we have the Z and the T formula, and then we also have the confidence interval for proportions. And since this problem is talking about the mean price charged for a trade of 100 shares at $50 per share, we're going to be choosing either the Z or the T version of that formula. The way you know which one to pick has to do with the type of standard deviation that is given to you. If you know the population standard deviation, which is sigma, that's how you know you're going to be using a Z-score to help you through that problem. So you want the confidence interval formula that has sample mean, which is X bar, and uses a Z-score in part of its calculation. So that formula, I'm going to write that down first, would be X bar, our estimate, plus or minus a Z-score that corresponds to our confidence interval, particularly the amount of area that's in a single tail. Remember, alpha is the amount of area in both tails, and alpha divided by 2 would be the amount of area in a single tail. And we take that times the standard error associated with the sample mean, which is sigma divided by the square root of n. So now we just need to find all of our different values. The sample mean, that was given to us here as $33.77, so that's going to be our X bar. We need to know sigma, so we need to know the population standard deviation, $15. We need to know n, which is the sample size. The survey was conducted annually, and we have a sample size of a sample survey of 54. So n is a 54. And then we need to find Z is the confidence level. The confidence coefficient, or the confidence interval, 95% would be 0.95 as a decimal. And from our previous lesson, we know that if 95% of our data is in the middle, then we're looking for 5% left over in the 2 tails. Remember, confidence interval is how much area you have between the lines. And we're trying to figure out the Z-score that corresponds with this location. So you need to know the amount of area to the left of that line so you can look it up in the Z-score table. So if we have 95% of data in the middle, that leaves 5% left over for both tails. And half of that would leave us 2.5% in the left tail, and we'd have that equal amount of area in the right tail because of symmetry. So we actually looked up in class together 0.0250 in the normal table, which is in the front of your textbook. And you look for 0.025 as one of the 4-digit numbers. And it's right here. Noticing that it's in row -1.9 and that it's in column 6, we can put that back together and say the Z-score that corresponds to that location is -1.96, and because of symmetry, the Z-score corresponding to the positive side is +1.96. After we go through a t-distribution scenario, we will have a shortcut for finding that critical Z value, which I'm going to start calling a Z star, just so it doesn't get confused with the Z-score that you calculate from the Z-score formula. So now we have our Z alpha over 2 number is 1.96, positive and negative. And notice that the positive and negative symbol is already a part of our formula. So all we're going to do at this point is just substitute numbers into their correct location. So 33.77 is going to lead off our confidence interval with our sample mean, plus or minus our z, critical z, our z star is what I'm going to call it. So 1.96, which gets multiplied by our sigma value of 15, which is being divided by the square root of our sample size, which was 54. This left-hand side here, the z-score times the standard error, that's called your margin of error. And if you multiply that and then divide, you don't need any special parentheses, you just type it in the way that it's printed on your paper. 1.96 times 15 divided by the square root of 5 and round to 4 digits, you're going to have 4.0008 as your margin of error number. Your plus and minus symbol is still in front of it. The 33.77 is still in the lead. At this point, what we want to do is go ahead and actually calculate the interval. So we're going to actually separate out this symbol, which means once go through and perform subtraction, the second time go through and perform addition. So if we take 33.77 and subtract the margin of error, 4.0008, we will get a total of 29.7692. And if we take 33.77 and we add 4.0008, that'll give us the high end for our interval, which would be 37.7708. A lot of times on a computer program, you're going to see those two numbers presented as an ordered pair, and they might state the confidence coefficient right above it as a column heading. What we want to do is practice writing an interpretation of what this sentence means. So remember that a confidence interval is with a certain degree of confidence. You think that not the sample mean, but the actual population mean of this scenario is found somewhere between these values. So we're going to lead off with our confidence. So we'd say I am, and our confidence level was 95%, so I am 95% confident. And then we want to bring in the population parameter. So the population's mean, and then you want to go back into your word problem and look at what your scenario was trying to figure out. It was trying to get a confidence interval for the mean price charged by discount brokers for that trade of 100 shares at $50 a share. So we are trying to estimate the population's mean price charged by discount brokers for a trade of 100 shares at $50 per share. Now it's kind of wordy, but it puts it in context. Is, and then you bring in your interval between, and because we're talking money, we're going to put dollar signs on our values, and you're welcome to round according to the type of units that you're working in. So if we're dealing with money, we can go ahead and make this $29.77, and our high end would be $37.77. So I'm 95% confident the population's mean price charged by discount brokers for a trade of 100 shares at $50 per share is somewhere between $29.77 and $37.77. So this is how we work out a confidence interval when we know the population standard deviation, which tells us we should be using a critical Z in order to calculate that. When you get into your second section of Chapter 8, you're going to learn about t-distributions, which are very similar to z-scores, except they're not as tall. They tend to be a flatter curve because of the smaller sample size that's usually used with t-distributions. But what we know is that they're very similar in value, and at infinity for a sample size, as you approach the largest sample size you have, the normal distribution and the t-distribution actually have matching values. So you could actually use the infinity row of your t-distribution table to find your critical z-scores instead of going through this long process of drawing out a picture, putting your confidence level in the middle, thinking about how much area is in the tails. All you have to know is how much area is in that tail. So once you know 0.025, you're going to use that as your column heading, the area in an upper tail, and you're going to travel to the infinity row of the t-table, and there's that 1.96 that we found going the more direct route. So this is just a shortcut. So most of our z-stars can be found again on the infinity row of the t-distribution table because of that connection that we have between a t and a z-score. So you again would just need to figure out how much area is in a single tail, figure out what column you need to be in, and then move yourself down to the infinity row of that particular table.